Welcome, everybody. It's my pleasure to tell you a little bit about our travel demand generation model called TAPAS and how it is linked with SUMO to produce combined results. My name is Matthias Heinrichs, and this whole work is based on from our Institute of Traffic Research, from Daniel Krajcevic and me. And of course, this wouldn't be possible if I wouldn't have got the big support from the TS team, and namely Michael Behrisch, Jakob Erdmann, and Thorsten Mollmann, who was in charge of the first time when we tried to put SUMOs and TAPAS together. Asian project we had. I think it's now 7 years old, and yeah. So why doesn't it work with the next slide to the next thing? Oh, my mouse is trapped. There, here we go. Okay. So first I give you a little bit about a little background, what we actually are doing here. Then I present you how TAPAS and SUMO are linked. And then I will give you some, because it's travel demand modeling, I will give you a short introduction and run through of 2 years of study in travel demand modeling in about 50 minutes. And then I will talk to you how we do the traffic assignment, the feedback, and present you some results we got from our projects we are doing with this kind of combination. First of all, travel demand modeling. If you're in this business, you most probably have heard about the 4-step approach, which actually consists of 5 steps, which is a little bit confusing. But it has trip generation, how many people are at a certain spot A want to do activity X, trip distribution, how many trips from A to activity X go to spot B, then and how many trips from A to B are go by mode M, and then which route from A to B is taken with respect to congestion, capacity limits, and so on. And as you know, SUMO basically only does the 4th step. So we take care of the first 3 steps. And then what everyone is missing, there is a feedback loop between this, because this is called what we call equilibrium, or something like a well-defined system, where our assumptions we do in TAPAS, like how long does it take to get there by car, does roughly meet what SUMO says when we're actually doing the trip, and we do not have any swing back effects or whatever. So what we are doing is an activity-based microscopic models, and you might ask, so why is the feedback so so important? Yeah. The travel demand model we using doesn't know anything about the road usage. So and you need the correct road usage to calculate the correct traffic times to evaluate if a trip is still feasible in certain time limits, or if a location is reachable in certain time limits. And yeah, so the principal operation here is it's quite, that's the overall flip chart. You see TAPAS and SUMO in the middle. Then we have a small extra model which we did not realize under open source yet, but it's planned to, which is called synthesizer. This is because TAPAS is doing trips for a synthetic population. So we get all persons for your study area. And we have a vehicle fleet for this population, and we somehow match it. This is all done by the synthesizer, and it's optional models. And then we take the population, put it into TAPAS, and TAPAS calculates trip chains for every person's, and flee and puts activity for us, which are basically what you're doing to do your regular work day, to fit locations to these activities, and to make a mode choice how you get there. And then you get a lot of trips for the persons in your study area. Then we feed these trips into SUMO. This is like this is strange. My monitor somehow or misaligned. I can't move my mouse. So we put this trips to Sumo, and Sumo then does the routing. Of course, we usually have additional traffic. That means we have through traffic. We have traffic we do not model, like post and like all the Amazon and DHL and FedEx and UPS cars down there, commercial traffic and so on. And we have network infrastructure information, and we put all this together, feed it to Sumo, and Sumo calculates us how these trips are actually performed. And then we can check if our assumptions in TAPAS are the same than the output of Sumo. And if not, then we get updated travel times and do the inner loop until we get to an equilibrium. So TAPAS, what it actually, you heard about it, it stands for Travel Activity Pattern Simulation. And it's an agent-based microscopic passenger demand model. So we try to model the individual mobility decisions and behavioral patterns for every person in our study area. And so every person is treated individually, but has a context of the household. So for instance, cars are usually a shared resource over the household. So if one takes the car, another person cannot take the car. And of course, you have trip chains in TAPAS. That means if a person starts its daily activities without a car, it cannot mystically beam its car from its home place to a location where it is. So it has to stick with non-car modes for the whole day until it reaches home again. And or the other way around, if you take the car, then you have to bring it back at the evening, because it's quite unhandy to leave the car somewhere in the city parked and no one knows where it is. And we're using this for long to mid-term effects, not the short-term effects. So what we are actually busy about is, what does demographic do to the city? What is if there a new area for industrial area is popped up in the city, and how does these change the mobility behavior of the whole city? And and you will see that some examples and a lot of more details at our GitHub address. You see it below. It is open source for now 1.5 years, but until now we doesn't have the popularity of Sumo yet. But we are catching up, I think. So second flow chart and about TAPAS is how does it work? You will see that there so now this is a zoom into the TAPAS bubble of the first flow chart, and see on the left-hand side there, there's a synthesizer getting synthetic population, and for every person on this population we choose an activity pattern. I will go through the blue buttons with additional slides later on. These activity patterns then go into a location choice where you get travel times, travel distances, locations, where are the locations and which type of the locations are there, and you choose a location combined with a mode, because it's usually locations are attractive only for certain modes, and so this is a combined choice we do in our model. And then we check the daily activity plans. So we check if the total travel time is still in a feasible range, if the travel costs are not exceeding your planned activity costs. And then we store it as a daily activity plan and just put it wherever you want to do, whatever you want to do with the daily activity plans. In our case, we just put it to Sumo and see what Sumo does it. So first thing is data preparation. TAPAS for itself is it's quite hungry for data. So the first thing you need is some kind of a synthetic population. Then we usually take census data and try to match other statistics like availability of public transport tickets, age structure, income structure, spatial distribution and all the stuff, and into this onto this population, and then we come out with a number of households, and they every household has, of course, a size, income, cars, and an address-based location. So TAPAS is on an internal level, we are working on address-based granularity. And then every household consists of different persons, consisting of age, gender, status, and every person, of course, has some mobility attributes like driving license, bike availability, long-term PT tickets, and some other stuff. But that's the basic attributes. Then, of course, you need some destinations, and unless the synthesizer roughly goes automatic, if you feed in the right statistics, the destinations are still in a semi-automatic generation process. This is because there's so many input over there. If you go for OSM is great for looking where are parks and playgrounds and some bars there, and points of interest, but you usually don't have capacities on there. So you don't know, is it a big bar or just this very small tiny bar? And you need to add some other data. And at the end, you get up with some attributes like type of destination, is it a working place, supermarket, doctor, bar, whatever, the address of the location, and the capacity. And finally, you need some infrastructure informations, and you can get this using GTFS data, OSM data, and put it into SUMO, or we have a tool called OMOAC, which is a little bit more convenient to get the GTFS data done up to now. And then you get some net information, which is in basically OD matrices, or that means origin and destination matrices for traffic assignment zones in your research area. So how does the trip generation work? Not traffic generation, trip generation. What we are doing is, let's start from the modeled region point of view. We have a modeled region, we have the households. Every household consists of persons and cars, and then we assign every person in this household some activities. And in Germany, we're using our national household survey. In American, there are other surveys, which, but basically you need a source of, we need of empiric activity plans. So that's usually travel diaries, and that's a good source for it. You can use other diaries or other surveys, but household surveys are usually the best source for it. And then what we're doing is we're grouping these household and these reported diary plans to certain groups that is basically some activity-based things that we said, okay, we put all diaries containing word trip in one group. And then we took all diaries that only contains shopping trip in another group. And then we do some subdivisions. That's how we group the diaries. And we do the same basically with the persons that you see on there on the blue bars on the bottom. These are, we have 33 person groups, which are basically divided by age, by status, that means working, non-working, retired, students, pupils, and so on, and gender and car ownership. If you have these groups, on the one hand, the diary groups, on the other hand, the person groups, we assign every person a diary by using probability vectors. So for every person group, there's a vector which tells you that this person group has a probability of, in this example, of 20, students have a probability of 20.1% of picking up diary group 21, and diary group 21 is education. And then you just pick up in your activity plans the diary group of which consists mainly of educational diaries, and then you have an activity plan for your day. Activity plan usually consists of something like go to university, go back, go to shopping, go back, visit a friend, and then go to sleep, something like this. or you can even have changed that you go directly from university shopping and then back. So after having some activities, you need some destinations. First thing is we've learned is that activities and locations are that they're not one-to-one convergent. There's no one-to-one correlation between them. If you look at big things like malls or pharmacies, you can do different things. At a pharmacy, you can do either shopping, like buying your new sunscreen, something like this, or you can do an errand, like the doctor set you with a recipe over there. Mall is multi-purpose location, and then there are locations where you usually have only a single purpose, like a cinema, which is purely leisure. Okay, it could be educational, but that's, I think, negligible for our purposes. If you have this mapping from activities to location, you have to look where can your people go. And this is quite complicated. That's why I have only some random slides, or it's not random, but this shows accessibility of shopping locations. But it tries to emphasize the problem over here, because if you're at your home, we actually do not know where you want to go. So what we tell you is that if there is a supermarket around the corner which has a capacity of 1,000 customers per day, then the size is not by coincidence, but it has something to do with the attraction potential of the supermarket. So the capacity of every location is somehow telling how attractive this location is. But of course, if the supermarket is very far away, like for instance Macy's in New York, then I will not go to it. Why that? That's because the distance to it is so long that it's simply not reachable. And then you in TAPAS you can choose between 4 different location choice models. Every has its own theory. If you're interested in this, I can provide you with some further notice, but it's we did not make any new invention over there. We just integrated state-of-the-art approaches into TAPAS, and you can select between 4 of them. So now what we have diaries, we have locations, and of course, as you see over here, locations have something like an accessibility. How can you get there? And of course, the accessibility is somehow computed by the modes of transport you can, which can be used to get there. So the mode choice is a rather complex model from the input data. But it's of course, first thing is we construct feasible trip chains, and that means the cars and bikes are only available at home and must be returned. But then when I go back to home, then I can choose for another mode if I take this mode fixed modes like cars and bikes. And every mode we dealing with in TAPAS, you see the list on the left side, has a total travel time, which is split up into 3 parts. First thing is access time. So, in case of bike time, this is the time you need to unlock your bike or get it from the basement or reach it wherever it is. And then the actual travel time, this is going from spot A to spot B, and then the egress time, in case of bikes, locking the bike and go from the bike post to the final destination. And this has several advantages because you can model a lot of things with these threefold of times. For instance, you can model park pressure, because park pressure usually determines the egress time of your, that means the time reaching a final destination and then actually getting rid of your car. And that's that's one basic principle in TAPAS. And if you have all these times, you get you come to mode choice. We use gold standard model over here, multinomial logits, and I hope that I'm telling you something new. It is this is basically that you are calculating the utility of each mode. So the utility is what bring the utility, and the cost of a mode is in theory it's the same. It's just the switch of the sign. So every cost is just a negative utility, and And you can integrate a lot of parameters in your cost function or utility function. And then the big challenge is to estimate the parameters which says how big the influence, for instance, of the travel time is for your mode choice. So the pros for these methods are that you have continuous integration of, for instance, costs, times, and age of the users, because age has certainly impact on certain modes, for instance, bikes or even cars. And you can integrate new modes via parameter adoption of known modes. So for instance, car sharing is not that much different from driving a car or taking a taxi. It's some more or less the combination of both. And then you just see what is the best mix of parameters between those two modes to get car sharing into your model. We had some papers showing that, how we did that. On the con side, you need to get a good estimation for these parameters. You need good and many data, and that's usually a showstopper if you don't have a good national household survey with 10,000s of trips. But there are ways to get around. Or you take the model from your neighbor group and then see how it works in your region. Of course, there's a higher computational cost. If you look at the formula on the right, you see a lot of exponential signs. And if you do this over and over again, and you will, and later on you will see that this next time you will see that we have to do it the billions of time. This takes time to compute, and E function is quite cost intensive if it comes to computational powers. And of course, you always have the problem of significance versus explanation. That means sometimes you have a parameter, for instance, age, and it is, and the model estimation says the age parameter is significant, but it's not the explaining parameters. For instance, age has a age in case of car driving usually shows you that you can obtain your driving license only from a certain age, usually 18 or 16. So there is, so the significance of age is somehow correlated to the driving license fact, and that means that the estimation finds out both facts, either the explanational part of your and some kind of hidden schemes behind it. But sometimes it's intended if you don't have any better idea what's going on, but sometimes it's misleading because you're mixing up 2 or 3 sources of knowledge into the same parameter. Okay, so I told you TAPAS is working on address-based level, and now I will tell you that we are using traffic assignment zones in TAPAS. So why lose this kind of resolution in our, here you see on the right hand, you see the traffic assignment zones of the city of Berlin. And it's that the problem is that we have to route a lot. And when I talk a lot, then I really mean a lot. It's we have 3.5 million persons in Berlin. Every person does a roughly 3.5 trips per day, and you have about 500,000 of possible locations where the persons can go, and you have 7 modes of transport. And if you multiply all these things, then you end up about 4.5 trillion routes. And even with a fast implementation of SUMO, with all effects you can do, you cannot end up with an computational time of 1 million days. And my contract is not running that long. And so what you need to do some grouping of TATSs after traveling analysis, traffic assignment zones, we call them TATS, and to simplify the whole thing. And to give you an idea what this means is, if you look at the 1,223 TATSs on the right, you have a little bit more than 1.4 million routing entries if you are pre-routing the whole system. If you look for all the possible 465,000 addresses, then you would end up with an OD matrix of 216 billion entries, and we don't have that much memory in our computers over there. It might be possible in future, but not for now. So what we do is we group our infrastructure on TAPAS level, which makes coupling to SUMO a little bit more interesting, as I will show you now. First of all, let's look what TAPAS, some output TAPAS is generating. The output of TAPAS is very boring. It's just a big database consisting of trip IDs with location, start coordinates, end coordinates, start times, a mode, and a car ID. But basically, that's all what SUMO needs to compute a feasible set of routes to put on the net. Of course, if you want to couple it with SUMO, you need some prerequisites for SUMO. Of course, first of all, you need to check out TAPAS-SUMO coupling from DLRTS GitHub site. You need a network, usually the net.net XML file, and you need a v-types matching, somehow matching your card types used in TAPAS with the card types used in SUMO. And for generating all your template folder and perhaps some pre-processing steps and post-processing steps, fixing traffic lights, junctions, defects, or whatever, you need some net config files. But usually you just need these three files, the net file, the v-types file, a net config file, and then you can generate and a set of file for a folder, actually a folder for SUMO, which is necessary to input all the TAPAS output into SUMO. If you want some feedback, of course you have to tell SUMO about traffic assignment zones you're using, and to speed up routing, you should put up some landmarks over there. Otherwise, it gets quite slow when you are if you are using big cities like the city of Berlin. So how does it work in detail? First, you start from the left point. You start with TAPAS. TAPAS gives you some TAPAS trips, as you've seen in the last slide, and you get perhaps you get some background traffic or no background traffic if you don't have it. We usually take this from our commercial traffic department, which tell us how many commercial trucks and delivery cars are going through Berlin. On the other side, you have the initialization of a network template, and you've done this with a Python script found in the TSC GitHub repository. And actually, what it does, it generates you a SUMO config, and then automatically triggers SUMO from the SUMO config, and SUMO calculates all the routes we are fed in. Then I usually go to sleep, and on the next day I have the results. And what is the result? Of course, I have trajectories for every trip I was planning. So I can check if the travel time SUMO is reporting roughly match the travel time I assumed when I was planning the TAPAS trip. And a second thing is, because I do not have trips from every travel assignment zone to other travel assignment zone, I need to do an all pairs calculation for the whole system and different states. So I calculate what was the state at 12 o'clock, give me the travel time for 12 o'clock, give me travel times for 8 o'clock in the morning, for 6 o'clock in the afternoon, and so on. And then I have new travel times for different system states, and I integrate them back into TAPAS. Of course, there we do some damping over there, which is mainly that I prevent oscillation in the system, because this is otherwise the changes would I would have like oscillation effect that there's a congestion of route A, and then the next run there's a congestion on route B, and so on and so on. Quite obvious, and so talking a lot about theory and how does it work. So how does it work if you put it together? Here you see the time deviation of different iterations. So what I did is I took my initial travel time and planned some trips, put in the trips and feed them back to SUMO, and SUMO gave me new travel times. This, the first iteration is the blue curve at the bottom. And you see that there was a deviation about 5 minutes. So the average, in average, my times were 5 minutes faster than SUMO predicted, which was feasible for the state because I started with idealistic travel times for the T0 times for midnight. And but after iteration 1, you got to the red curve, and all of a sudden the planning times didn't deviate that much from the times SUMO set in the second run, which means that TAPAS was rerouting and reconsidering all location and mode choice and adopted to the new travel times of SUMO, and SUMO told me, yeah, with these demand, I can give you travel times which are much more likely than the times you were expected. And from that iteration on, we did it. You see that we did it 5 times, and all further iterations did not show any further improvement. So after 3 iterations, we were ready, and we had a state of equilibrium. We had a deviation of plus minus 1 minute with an median value of 0, which is great, and we had a stable system that SUMO and TAPAS were somehow judging the traffic in our research area the same way. So yeah, but that's some. You tell me, but how valid is this? And then we examined what is the actual output over there, and we had some traffic counts on certain roads, and we compared it. What is our demand we put in, and what is the demand reported on the those counting spots on our usually on our the counts. The spots where the city of Berlin is counting are usually the inner highway, big highway crossings. And that's why it's always the highway density we're showing here. And as you see that the reported values are the light gray, and then you see the 20 and 80% percentile quantiles around it, and the green line is the SUMO result of it. And as you see, the travel demand we have generated very nice fits to to the demand which was reported on the streets, which gives us a good feeling that our approach is justified, and we can tell you how congested the streets and the cities are. Yeah, and yeah, so I just gave you a very brief overview how what TAPAS is capable, how the input data of TAPAS is prepared, which module it consists, and what actually the results are. It's complete automatic. If you do the right configurations, tell SUMO which simulation to use, and then you can get a full combined loop between both programs and get nice results, which take congestions into account if it comes to daily activity planning. And with these slides, I would end and are free to answer questions.